Hi, this is Mike Henriksen from Fluent and Velocity in San Jose. I'm here with Bernhard from Intel. Bernhard, how are you doing?
Very good. How are you, Mike?
I'm doing well. So you talked about FPGAs today, or Intel talked about them on the stage. Velocity is kind of a different kind of audience. What would you like those people to understand about Intel and FPGAs?
Mm-hmm. A lot of the users here are really software developers, and they may ask, what's an FPGA? Right?
Exactly.
An FPGA is two things: field programmable gate array. So it's a gate array, which is an array of hardware blocks, highly interconnected with each other. And these hardware blocks are programmable, and the interconnect is programmable. So what you can build is a custom hardware function on the FPGA, and some call it software-defined hardware.
Okay.
And that what allows you to do is you build your custom hardware function in a highly parallel way.
So why would someone want to have a software-defined hardware device or system?
So FPGAs accelerate compute because of the massive parallel architecture they have, that you can really run compute algorithms very efficiently on this parallel architecture. You get much higher performance, lower latency, and power efficiency as an accelerator. So people are putting FPGAs into the data center and the cloud to accelerate specific workloads for compute and networking acceleration.
And can they scale that as well? Is it make scaling easier or difficult, or how do you manage that part of the FPGAs?
Usually the FPGA is attached to the CPU, and the CPU is being scaled out in the data center, and so do we do it with the FPGA as well. Now, what's important there is, how do you make an FPGA now usable as if it were a CPU in the data center? Because FPGA is programmable hardware, and the traditional design flow for FPGA is very hardware-centric.
So is this also going to be really important because of IoT? I mean, to me it sounds like this is a play that's going to bring hardware and performance and, I'd hope, security and everything together.
Mm-hmm. Well, acceleration with FPGA is not only a matter in the data center and the cloud. FPGAs are being deployed all the way to the edge, where it gets closer and closer to some of the IoT applications, such as autonomous driving or security, cameras, and things like that. So FPGAs, due to the nature and the hardware acceleration they can do, they span from edge to cloud.
And so how do people, let's say a DevOps person, how do they get more information and understand how to start programming, how to build with FPGAs? Mm-hmm. How do they get going doing that?
Well, there's different user personas. Let's take the cloud service provider, for example. How can they enable an FPGA as any other compute resource they have in their data center, right? And we do this by abstracting the low-level programming and management of the FPGA away through providing drivers and APIs, which then allows the cloud service provider to use hypervisors and virtual machines to access the FPGA, and then integrate this into their common orchestration frameworks. So for the cloud service provider, the FPGA looks like any other compute resource, like a Xeon or a GPU or others. Right?
So it works with any cloud provider? It's going to work with Google, Amazon, Microsoft?
It does, yeah.
Everyone?
And many of those are already using FPGAs at scale in their data centers.
So what are the biggest benefits for, let's say, an organization that has a massive amount of data coming in and going out? Mm-hmm. What is the advantage of an FPGA?
Mm-hmm. Because of the architecture, as we discussed before, and the ability to, in parallel, execute algorithms very efficiently on that hardware, they can accelerate certain workloads very, very efficient, and that basically allows them to offload a lot of the compute from a general purpose device like a CPU to the FPGA. And that gives them higher performance, and what they often measure in is performance per TCO. They get more compute at lower power, hence lower cost for the data center operator.
And higher performance doesn't mean they're going to take a hit on reliability or resilience or anything like that, because it's all built into the FPGA? Is that?
Well, as the FPGA itself has mechanisms and ways to protect, and to offer resilience like any other of the devices. So that's been taken care of.
So is this a huge move for Intel? I mean, is this something that's going to revolutionize a lot of what you guys are doing?
Absolutely, right? When you think about the opportunity here is as we have to compute, if we create the experiences, the application, create more and more data, and we need more and more compute to make sense out of that data. An application like autonomous driving or AI is a big one as well. We believe that FPGAs will be deployed at scale in the data center as part of the hyperscale build-out, and therefore it's a huge opportunity for us.
Does this help with Moore's Law? Because I know we used to build faster and faster chips every year to combat Moore's Law creeping up on everyone. Are FPGAs going to be that for large data deployment?
Well, Moore's Law is going to continue, and FPGAs are always built on the latest and greatest technology because we want to drive performance up, we want density, we want more capability. So we're following and leveraging Moore's Law specifically at Intel now that we're building the FPGAs on Intel process technology. But when you look at the data center or the applications, what you'll find is it becomes more and more heterogeneous. You have purpose-built accelerators and processing elements in there, and the combination of the two will give you that boost in compute you need to enable these new experiences.
So what tools and resources are available for developers to learn to develop and design and deploy on your FPGAs?
So, of course, we continue to provide the more hardware-centric development tools for the traditional hardware engineer, but increasingly software engineers want to take advantage of the FPGA, right? And for those designers, we offer what we call high-level design tools like OpenCL or high-level synthesis, where they can program the FPGA from an environment they're very used to, from C++, for example, right? In addition, we provide enhanced libraries, now FPGA-enabled libraries such as MKL, MKLDNN, DAL, or DPDK, which traditionally target other Intel devices. We've enhanced them now to target FPGA, so that the designer can now directly target the FPGA. And because these libraries are also being used by the higher level frameworks, for example, TensorFlow, Caffe for AI, or Spark Hadoop for data analytics, they can now also target FPGA because we have enhanced the libraries, and that enables the software developer to stay in their environment they're used to programming.
What is the easiest way for a developer to find this information? Is it just Google for FPGAs and Intel, or
go to the web and you'll find a lot of that on our websites.
So Bernhard, if we sat down next year here in San Jose and had a discussion about your journey from where you are today with FPGAs and where you are 12 months from now, what would you say you guys have accomplished in that 12-month period?
Whereas my mission in life is to put FPGA in the software developer's hand, and in doing so, enable FPGA benefit at scale in applications like in the data center and in others, right? So the tools we build here, the APIs, the libraries we build, integration into frameworks and SDKs, to provide an environment where a software developer can take advantage of the FPGA in an environment they're very, very familiar with. That is a key mission I have to enable that. And I believe that in doing so, I get much more FPGA adoption in these environments than before.
Excellent. We look forward to that journey.
Okay, thank you.
Thank you.
Thank you, Mike.